So hello to everyone, welcome to my talk. My name is Lubomír Štěpánek. Thank you for a very nice introduction and invitation. So I just came from the first faculty of medicine, Charles in Prague, and also from faculty of informatics and statistics, University of Economics in Prague. And together with my team, we are interested in various topics, somewhere in the middle between computer science and computational statistics and classical statistics too. This is also what I will be talking about for today. So I'll talk about a way how to use random forest-based algorithm to, let's say, do some inferential testing or post-hoc testing, which is usually done by some very traditional methods, but those methods are usually limited by some rigorous statistical assumptions. So I would like to, let's say, introduce or propose an alternative to those traditional methods. And of course, it's a big pleasure for me to say this is just a joint work with Filip, Habarta, and Ivana and Luboš, Marek. So let's have a look at the outline of my talk. So I will introduce very basic terms which are important to know, also what is the motivation to do this kind of study. Then I will revisit some basic principles, basic ideas which are behind the analysis covariance and post-hoc testing. I'm not going too deeper into some details because it's not even important for my talk. Also, I revisit some tree-based and random forest algorithms. Also, I'll just pick on the important piece of knowledge which could be handy for, let's say, interaction of our proposed method. Then I'll talk a bit about the proposed method, of course. This is what my talk should be about. And finally, I will try to show or confirm some expected properties of our proposed method by some simulation study. So regarding motivation, so let's suppose that we did some kind of regression model, which is called ANCOVA, analysis of covariance, very commonly used kind of model, and it's pretty similar to linear regression, nothing too different. So you have like a continuous variable, dependent variable, and you would like to know a relationship between some other kind of continuous variables, which are usually called covariates, and also some categorical factors. So you want to know whether there are some significant relationships between the dependent variable, for example, your wage, and some other kind of variables like, for example, gender or let's say level of education and so on. So this kind of classical models. And ANCOVA, like analysis of covariance, which is a kind of linear regression model, can tell us or can answer us a question whether there is a significant factor which has some significant influence on the dependent variable. This is what ANCOVA can do for us. But the problem is that whether, in case that ANCOVA can identify this kind of factor, one or more factors that are significant for the dependent variable, there is another kind of question, the second question, which is totally feasible, and we would like to know which categories of these category factors simply differ within their means, within their averages. So if we just put two subsamples or two all the observation which belongs to two different categories, we are about to calculate averages of the dependent continuous variable for those two subsamples, and we would like to know whether the averages of these two between these two subsamples are simply differ substantially or not. So this is the question, and to answer this second kind of question, we can use very traditional kind of methods which are listed there. It's like a two-case analysis difference, HSD test, or Sheff's test, or Dunn's test, or Nemenis test, and many others. Maybe you know from your experience that if there are plenty of methods to do some task, no one of them is just perfect. So each one of the methods has some advantages, but also some disadvantages. So sometimes it's pretty hard to decide which one to use. Sometimes you can even get into some very strange situation that, for example, ANCOVA may identify a significant factor for you, but each of these post-hoc testing methods will fail to identify, let's say, any kind of pair of categories which could differ within their averages. So it means that you will just end up with two, let's say, two claims that are in contrary. Based on ANCOVA, there should be like at least one factor with at least two different categories. And based and using the post-hoc methods, there seems to be no one factor which should be significant and no two categories which should differ mutually. So problem beside the decision which kind of the post-hoc test which we should use, there's also a kind of problem that of course these threshold methods are very limited by some statistical assumptions. They are pretty rigid. So what we did in this study, we just tried to address this kind of issue, and we refined the task using kind of forest-based algorithm, which is we know practically in practice assumption free. And it works on the very easy idea, basic idea that we simply classifies all the observations of the factors, of the significant factors categories. We try to classify into these categories, and if there are, let's say, high proportion of all trees in the random forest that classify into these two categories, then we have some evidence, or we could think that, okay, it seems that those two categories are really different, because random forest algorithm based on multiple trees is able to classify into these two categories, or even more categories, but at least these two categories of given factor. And the given factor was primarily an input variable for the ANCOVA, but now it's an output, like leaf node variable for the random forest. I'm just going to talk about it. So quick revision. Okay, what we can see in the formula is just a kind of linear regression. Here you can see that we have some kind of dependent variable y, some grand total mean. Then there are some, let's say, delta levels, which stands for each one of categorical factor variables. Also, there are some covariates, continuous covariates. There are m of covariates, which has their linear regression coefficient beta, and some continuous values x, and there is some disturbance or some residual term, of course, because verb is not perfect. So we have to address the thing that there are some, let's say, inaccuracies in measurements, or some kinds of inner variability which is not able to be explained by the model, and so that's why there are some residual terms. So it's kind of kinds of regression model, nothing new here. How does it work? You know that we can try to calculate total sum of squares for the dependent variable, and per each of m covariates we have to reduce it by this term, which is equivalent or proportional related to the to its regression coefficient. So in the very end, we are able to get a total sum of squares with asterisk, which is decreased by the summation, and the summation with asterisk is then decomposed into residual sum of squares and into a sum of squares which stands for given factor. And the given factor is simply tested by ANOVA, analysis of variance, Fisher, Snake, or ANOVA. Nothing new here. It's not so much important to understand the, let's say, the equations at this moment, because this is not what my talk should be about. But this is like a commonly used 100 years old theory, and it works. It's applied on daily basis. There's nothing new about it. So ANCOVA is something which works, and as I told you, like in practical point of view, it's able to let's say to answer the question whether there is at least one factor which is important or which is significant for explanation of variability of the dependent variable. So, for example, it could be on some practical example that, as I told you, that we could, for example, let's say, test whether my wage or my monthly income is, or whether our monthly income is dependent on, let's say, education level, yeah, which usually has $3. I think it usually works that, for example, people with college education usually have a higher income. So this kind of factor will be identified very likely as a significant one. So ANCOVA also is limited by some assumptions. Maybe you know it, this kind of assumption, this bunch of assumptions as a white noise. It's typical in technical sciences, it's called white noise. So residuals should be independent and identically distributed. Yeah, and ideally they should be also normally distributed. But the second part of this kind of analysis is that, for example, okay, let's go back to our example. I identified that education levels is important or significant for explanation of my of our monthly income, and we would like to know where exactly is the difference, for example, between higher or grammar education level, or for example college level, or high school level. Where exactly is the difference? So to address this question, we can apply some of post-hoc tests, and there are at least 4 of them which are commonly used. But in fact, there are about 10 or maybe 20 of these methods. So as I already told you, it's sometimes hard to decide which one to use. So it's not so important to go into the mathematics, into the equations here, but it works on the basis that we just simply calculate averages of 2 categories that are compared, and we are to plug it into this inequalities, and whether the inequality holds with some level of confidence, we can say that okay, those categories have significantly different averages. Yeah, so we can use Tukey significant difference test, or Shepard's test, or Dunn's test, or Nemenis test. It doesn't matter, because either the formulas differ a bit. But what is important to say that all of these methods are limited by assumptions. Some of them are limited, let's say, not so strictly, but if they are not so much limited, they are almost assumption free, then in such a case, the problem could be that they have pretty low statistical power to identify the statistically important or significant difference. So there are still some problems, and even more, there could be a strange situation that no one of these methods can identify at least 2 categories that differ in their averages. But still, we know from ANCOA that there should be some pair of these categories. So this could be an issue, and this issue is not addressed so far by classical statistics. So we are slowly moving to the proposed method. Each one of us know everything about decision trees. So you know that decision trees is just a smart data set partitioning. Yeah. So we have a data set. We have some dependent variable, which in this case is categorical, and using some criteria, some metrics, which is usually minimized within each step. We are about to partition the subsamples into new subsamples, and this is repeated again and again until for each leaf nodes and leaf branches, let's say the proportion of target classes is almost 100%, or if we are about to overfit the decision tree growing, there's also 100% proportion of target classes in the leaf nodes, but this is not so good, of course, to have overfit trees. So fancy thing about this is, of course, that we can plot it using very fancy kind of dendrograms. So yeah, it works, and this is also a relatively old methodology. Okay, let's denote sigma, proportion of target class of all observations in a given leaf node NT. And of course, we would like to have, like in ideal world, that for each leaf node there should be only observations of one target class. In such a case, our tree is perfect in the meaning that there is no impurity for no one of the leaf nodes. So sigma this proportion should be maximized. So we are about to say that for the leaf node NT, it is going to classify into class J asterisk for argument maximum of all possible classes. So simply the proportion of the most frequent classes in a given leaf node is D1, which this node is going to classify into. And the criterion which is minimized when the tree is induced is usually called impurity measure, and there are some of them commonly used, either misclassification error, which is simply 1 minus the proportion of the target class, or Gini index, or deviance, which is in fact channel entropy, you can see. And of course, the higher is the proportion of a target class the leaf node is classifying into, then each one of these impurity measures is going to be minimized. So we are about to minimize these impurity measures to ensure that just a guarantee that the tree classifies relatively well. But the problem is, and you know it, that typically trees tend to overfit, because you know that if there's at least two different classes in the leaf node, there's still, if there is no stopping criterion, the tree is still going to partition and partition again and again until the very final moment that there are, for example, at least one observation in the leaf nodes, but those observations are for given classes. So this is the way how we can ensure like totally perfectly classifying trees, but those trees are typically overfit. So how to avoid the overfit? This is a formula which I cited from Hestiti Pshirani machine learning book. Definitely know it. It's a rather introductory book, but still good. And it's called cost complexity function. We are about to minimize it just to find a subtree. So the first part of the summation is usually we cannot influence it much, because there is just a number of observation for given leaf node nt. There is just a value of impurity measure. But what we can relatively easily manage is the second term in the summation, which is like a kappa parameter, penalization parameter, pruning parameter, and simply a number of leaf nodes. So this should be minimized to find a final subtree which is not overfit, hopefully. And if the kappa is very low, it means that number of leaf nodes of the tree could be pretty high. In such a case, the tree is very complex and tend to overfit. So kappa shouldn't be equal to 0. And if on the other hand, kappa is pretty high, then to minimize the whole formula, number of leaf nodes should be pretty low. So that's why by choice of kappa we can try to influence the behavior of tree pruning and tree induction. So this is what I'm going to use also in my method. So random forests are pretty easily. If you know how to let a tree grow, then if we have just a family or bunch of multiple trees, we have random forest. Two things that first we mentioned is that first is that just to ensure that all the trees are mutually different, or at least not very similar, we have to use bootstrap just to pre-select some pre-selection or sub-selection of all the leaf node variables, just to ensure that the trees mutually differ a bit in random. Because, for example, from some number of trees in a random forest, there should be absolutely infeasible to add new trees, because of the fact that all the new trees should will be totally the same like the pre-existing trees, because of the fact that of course, the number of combinations is limited. So we have to use bootstrapping to ensure that they differ a bit. And the second thing is that the final classification using random forest is done by voting scheme. So if there's in 1,000 of trees in a random forest, there are 600 of trees classifying into one class. This will be like the final class, target class for the given observation. So the proposed method, what is the basic idea? It's pretty simple. So there are two examples of trees. The left one is very simple. It's just a root node tree, and you can see that regardless of the value of capital X1 variable, it's going to classify into this superset of category CR and CS. So it's in other words not able to distinguish between these two categories. The right hand side image, this is also a very simple tree, but a bit better than the left hand side one, because if capital X1 variable is higher, greater than or equal to X1, then it can distinguish between category CR and CS. So it's possible to distinguish between these categories. And if you have like a random forest model consisting of let's say 1,000 or some number of trees, and those trees are rather like the right hand one, so they are able to distinguish between these two categories, then we just got some evidence to think, okay, it seems that those categories really differ, or could differ. Of course, it depends on the kappa parameter and some other tuning parameters, but this is like a basic idea. So if there are really like a majority of trees, like the left hand side one trees, it's not able to classify into those into these two categories. But if there is like many trees like the right hand one, it could classify into these categories. So we have to do some let's say switch or refining of variables. So our factor variables, which was initially input variable for ANCOVA, is now output variable, so a dependent target variable, it also say target variable for the trees in a random forest. And all other variables like the original dependent continuous variable, covariates, and other factor variables, those are now input variables. So those will serve as a node decision rules variables for the tree induction. Okay, inference behind this method is also relatively easily. So null hypothesis H null simply claims that there is no statistical difference between the categories CR and CS, and alternative hypothesis claims the contradiction. And also we have to revisit the p-value term. P-value is just probability of collecting data at least as extreme as the data actually observed under the assumption of null hypothesis. So now what is important? So let's mark as TC a number of all the trees in our forest that are in contradiction to null hypothesis. So those trees that are in contradiction to null hypothesis are the trees that are able to classify into the given two classes, CR and CS, and also maybe into some other classes, it doesn't matter, but at least into these two classes, CR and CS. So number of TC is just simply a number of all the trees that are able to classify into these two classes, so they are complex enough to classify into these two classes. And also let's mark as a T number of all trees in a random forest. And now we also are about to need an identifier that will return number one if and only if the tree tau classifies into the category CR and CS. Otherwise, it will return 0. So TC is it's obviously equal to summation of this identifier because it's simply a summation of ones and zeros. 0 stands for the trees that are not able to classify into CR and CS categories, and ones are for the trees that are able to classify it. So let's use the definition of p-value. So p-value is just a probability of getting data at least at the observed data under a null hypothesis. So it's just simply a probability that you just have a number of trees that are able to classify into these two categories or maybe some others should be greater than or equal to TC, yeah? Because at least as extreme. So sorry, as I see under null hypothesis. So it means that if you are just assume that the trees are independent, this is why are trees in a random forest independent? They should be independent because they are just boosted before, so they should be, or at least relatively well independent, and they not like 100% independent, but should be relatively independent. So so the possibilities that there are at least a number of trees classifying into these two categories, like if there are TC or TC plus 1, TC plus 2, and so as T trees classifying into these two categories. And if those options are equally likely, we can simply calculate probability as a set size of this number of options divided by number of all trees. So it's T minus TC plus 1 divided by T. So it's pretty easily a nice formula, which is not really easily derived. So some behavior of this formula, or p-value. So if a number of TC is relatively low, it means that the random forest model is not able to classify in average, like in total, too much into the null hypothesis, into those two categories. So it's in agreement with null hypothesis. And early, if TC is very low, this number tends to be 0. So 1 minus 0 is close to 1, which is not below the alpha level. So null hypothesis not to be rejected, which is in agreement with the null hypothesis. And vice versa, the number of trees TC is high, number of trees with high sufficient complexity. It means that random forest is in contrary to null hypothesis because it's going to classify into these two categories with many trees, and it's simply an opposite to the fact that those two categories shouldn't differ in their averages. So then 1 minus this term is like pretty close to, because it's 1 minus 1, because TC is relatively high. It's like almost equal to T. So 1 minus 1 is close to 0, which is very likely below alpha level, and null hypothesis will be rejected, which is in contrary to null hypothesis, of course. And what is the role of kappa parameter? So going back to the formula from Hesti-Tibshirani. So if kappa is equal to 0, we know that there is no penalization for high complexity trees. So many trees, maybe all of the trees, are going to classify into all categories, including our categories CR and CS. So TC is almost equal to T, and by doing the arithmetics here, we just got 0, which is for p-value, which is very likely below the alpha level. So we are about to reach the null hypothesis, which is according to our expectation. Also, when kappa is relatively high, it's hard to say what should be like the ideal value of kappa, because it's data driven, yeah, partly. So this complexity will be generally lower because there's a penalization, non-zero penalization for complex trees. So some of these are able to classify into those categories CR and CS, but some other trees are not able to do it. So it's hard to say whether p-value will be below or above the alpha level. So then it's relatively hard. So it has to be, let's say, simulated numerically, very likely. Okay, time complexity is based on time complexity of tree induction and random forest. So if it's pretty based on how well the data set is balanced. If our data set is very well balanced, it means that by each data partitioning, we'll just get roughly 2 subsamples which are roughly half and half of the original data set. So it's like half and half, and then half and half of halves, and so on and so on. So this is proportional to powers of 2. That means that the best case scenario is proportional to logarithm with base 2 from a sample size. And the worst case scenario is the data set is totally in balance. So by each partition, we are about to remove only 1 observation. So we have to do it n times because there are n observations. So the worst case scenario is proportional to n, and it's multiplied by a number of all variables, because within each partition you have to search for the universe of all variables, just to search for node rule, and also through all observations. So it's a multiplication of number of variables and number of observations. So this is like the time complexity for one tree induction. Since we have t trees in a random forest, it's simply multiplied by t. So it's easy. But the good piece of news for us is that it could be parallelized. So if you have, let's say, 16 cores on your device or server or cloud or grid, you let's say you can have pi independent slavers. I'm not sure whether it's correct to say slave process now in a conference, but okay. I'm just kidding. Master slave paradigm, you know. So it can be divided by pi, of course. So we can, for example, speed it up, for example, by a factor of by number of your cores. And simulation study, last 2 slides. We wanted to compare our method with the traditional post-hoc tests. So we generated 1,000 data sets, and we compared whether for slowness factor, which should be significantly, which should include significant non-different averages, whether our method or other methods, they are just going to claim that there is a significant difference. So this is a kind of false claiming, because of course if there is no significant difference, those averages are totally the same, they are generated as the same. So claiming there's a difference is a situation which is called first type error. So we are about to calculate first type error rate. And of course, we repeated the simulation for different values of kappa parameter, just to determine how kappa parameter can, let's say, influence the first type error rate. And this is not so interesting, but the data were generated by following some rules, just for reproducibility of the simulation. So usually all the covariates or the dependent variable or some factors should follow normal distribution. That's not for our method, which is almost assumption free, but this is regarding the traditional methods that some of them will totally fail in case that they will be not normally distributed. And this table is like a result of simulation. What is important, the 2K ASD test, Scheffer test, Jan test, and Nemesis test, all of them you can see that the first type error rate is somewhere about 0.05, which is like a preset level. So there is no nothing interesting about it. But what is interesting that our method, random freeze testing, if we are about to increase the kappa level, you can see at the level of cases when p-value was below the alpha level, simply decreasing. And first type error rate also decreases once kappa increases, which is pretty logical, because if kappa is high enough, it means that there's penalization for pretty very complex trees in our random forest. It means that some those penalized trees are not going to much complex, that they are not going to classify into the two categories that are compared, and that's why it's failed. Okay, it's maybe in this case it's not failed to identify the difference, because there's no difference. It's simulated as two categories with no different averages. So seems to work. So we can, by increasing kappa level, we can simply reduce the first type error rate, which is also proved by the simulation. Simulation is not a proof, of course, but it can give us some more confidence of how it works. So just to conclude this, so Ankova works somehow, there's no problem, but if you like to do the post-hoc testing, you have to you simply have to decide whether to use Chefetes or Danes or many of them. It's hard to decide which one is best. You can do all of them, but problem could also be that if some of the post-hoc testing are just claiming something else that other the rest of the post-hoc testing. So we just introduced alternative to this, which is based on random forest testing. We have to switch the variables, so our factor variable, so that two categories are compared within this factor, is now leaf node variable for the trees in the random forest, and all other variables from Ankova are now like node rules categories, so input variables. Also, we derived that p-value can be estimated as a proportion of trees that are with sufficient complexity, that are able to classify into two or more categories to all trees in the forest. And also what was mentioned is, sorry, the parameter kappa, I'm not able to do it, sorry. Sorry. Okay, we are good. Okay. Parameter just determines the forest tree's complexity. So if the kappa is increased, we know that the p-value increase, the p-value was in average like also increased, and first type error rate was reduced. So this is the way how we can control the first type error rate. And also a good thing of good piece of news is that the random forest method is practically assumption free. So thank you for your attention. And if there are any questions, I can try to answer them. So start shooting if you want to, not literally, of course. Okay, thank you for attention.
Do you plan to work further on the method and improve it? So do you foresee any future works?
Definitely. Besides the publication, of course, this is also part of my thesis. So I have to implement. It would be nice to implement it as, for example, package to R language, for example. This is my plan, to implement it. And yeah. Of course, there are some disadvantages, because, for example, sometimes if you have a very low number of variables, then our trees in our forest are okay. You are limited in number of trees in our forest, because if you have pretty low number of variables, then the bootstrapping within the random forest is pretty limited. So there are also some disadvantages, because okay, there's no method which is totally best there. So there are also some disadvantages, but I would like to implement it as an R package, as an alternative to the classical methods.
Yeah. Okay, make it available.
Okay.
Very nice.
Thank you.
Thank you very much for the. One more question.
Yeah. Of course.
Are there any alternatives, besides these forests in order to solve the problem in the
Yeah. You mean like that I can just take pencil, paper, and calculate the or just enumerate the inequalities and to say that okay, these two categories seems to be different. Do you mean this? Yeah. Okay. This is an advantage of those methods, of course. They are pretty quick. Yeah.
New methods which somehow can be implemented or are implemented and used.
Those methods, like the traditional one, like the Chefetes and so, those are already implemented. Yeah, those are because those are pretty relatively old, old but gold. But yeah, I don't know if I got your question. So you are asking, maybe can you repeat it, please? I maybe didn't get that. Yeah.
Any alternatives to random forests?
Sorry, to random forest. You mean like to post-hoc testing using random? Okay. I'm not sure because I just went deeper in the problem of post-hoc testing. I tried to implement this random forest method, which seems to be new. There is no much evidence in literature so far, but I think that there could be some. Okay, how to say? I think that in literature there are like totally new alternative besides random forest method and the traditional methods. I think that in literature there are like no other kinds of alternatives because like I think that usually statisticians use the traditional methods because they are really quick. Yeah, they could be calculated by pencil papers, as you mentioned. But yeah.
You said that you could use decision trees. So you could say decision tree is a simpler method of random forest, but then for random forest you got it better, and you prove that in your presentation, right?
Yeah.
So you could say decision tree is also a possibility, but it's not good enough, maybe.
Yeah. Okay. Okay. If you just for example use only one decision tree is able to let's say to do the classification. But the problem is that if I'm about to calculate a p-value, I have a bunch of trees because of the as I try to I have to some number of these t, which was like my that's why. An alternative could be that, for example, I could like try to think out, or anybody could think about it like that we can use a different kind of classifier because there are many classifiers like neural networks or whatever or supervector machines. But the nice thing about trees and random forest is that random forest is like natively ensemble because it consists of multiple trees. So it's nice thing about random forest. Yeah. But okay. From my feeling, from experience, from my feeling is that if I just try to combine another kind of classifier, it would be too much complex, and the mathematics behind it will be too much difficult that it wouldn't be so easy to derive the formula for p-value. Yeah, that's my point of view. But of course, for some other team could go deeper into this, and maybe they will be successful with this. Maybe this may be possible. But for me as a statistician, it's too difficult to do a relatively simple task like post-hoc testing. Yeah. But thank you for a question. Yeah, good question.